Once we know the change of the position, we will next define the rate of change of the position. So we will first define the average velocity. The average velocity. By definition, the average velocity delta x, v a v g v x a v g is equal to the delta x divided by the delta t. So we can see that from this definition, the average velocity gives you the information of the rate of change of the position. Okay. Anyway, we call it the average velocity because it's not give us the very detail of the motion. It just gives us that in the time interval delta t, the displacement change delta x, and the average rate of change is delta x over delta t. So that's why we call it the average velocity. Okay. We also define the average speed. The average speed, which by definition VAVG is d over t. Okay, you can see the notation are different a little bit. For the average velocity, we have to specify x here to know that it is the average velocity in the x direction. But for the average speed, you don't have to specify the direction because the speed is the scalar. So we just measure the length. It's nothing to do with the direction. So we have the notation like this for the average speed. Graphically, we can represent the average velocity by the slope of the straight line that join 2 points, the initial and the final point of the motion. Let's see this graph. Okay, if we look at the graphical representation here, and if we are interested in the motion of the particle from point A to B, you can see that by graphical representation, the displacement is the length of this line. The displacement is the delta x is here. Okay, this is the delta x. And the delta t is here. Okay, and when you draw the line joining A to B, the straight line join A to B, the slope of this line is delta x over delta t. So by definition, this is the average velocity. Okay, so from the graphical representation, you can calculate the average velocity from the line joining two points. Okay, the slope of the line joining two points in the graphical representation. There is a pitfall that you have to be careful on the average speed and the average velocity. You can see that the magnitude of the average velocity is not the average speed. Okay, we cannot say that the average velocity is the magnitude of the average speed. We cannot say that the average speed is the magnitude of the average velocity. Okay. For example, consider the marathon runner discussed before in equation 2.3. The magnitude of her average velocity is 0, but her average speed is clearly not 0. Okay, this is equation 2.3 in the book, but we can also see this in our example before. For example, if we look back to this picture, this is the same. When the basketball player run from this side to the other side, run back, if you want to calculate the average velocity, it is the xf minus xi over delta t. Okay, so we have that the Vx a Vt is equal to the delta x over delta t, which is equal to xf minus xi over delta t. But in this case, you can see that the xf minus xi is almost 0. So it means that the average velocity is almost 0 too. But you can see that the player run with some amount of speed, but the average velocity is almost 0. But if you want to calculate the average speed, you can see that the average speed is d over delta t, which obviously positive and can have a large value. So you can see that the average speed can be very different in magnitude to the average velocity. It means that the average speed is not the magnitude of the average velocity. Many students misunderstand this and think that the average speed is the magnitude of the average velocity. Okay, so be careful on this point.